All right, workout number 3 for lesson 28. I've redrawn the diagram here with all pertinent information coming out of the problem, but it is worth noting that this is a frictionless table. We'll need that in a second. So the first thing we're going to want to do is to define in our problem um, some coordinate system along with our picture. So it appears that the 1 kilogram block is going to fall towards the ground, so that seems like a good way for us to define our system. So we'll define positive as that way. Now let's look at the problem. In the hint, it even tells us that this is going to be a Newton's second law problem. So we've done these before. This time, though, we are going to have to include the torque as well. So in any Newton's second law problem, we're going to want to start with free body diagrams. So let's go ahead and do that first. So we're going to need for, let's say, block 1 here, we've got two things acting on it. We've got force of gravity and we have tension 1 there. And based on the coordinate system that we've chosen as positive going towards the ground, that way is going to be positive for us as well as that way with y and x there. All right, now for block 2, we have the normal force from the table. We have gravity pulling down, and we have tension 2 pulling us towards the edge of the table. Now, it is a frictionless table, so we don't have any friction resisting that, pulling it back. And then lastly, we're going to have to look at the pulley as well. So the pulley here, we've got some radius, right, away, but we have tension 2 pulling us towards the block 2, and then we have at some radius away, we also have tension 1 pulling us down. And you can imagine if we were to draw in our, it's not quite centered, but you get the kind of the idea of where those radiuses come from on that pulley. Oh, and we forgot our coordinate system on mass 2 here, but those two directions are going to be positive with x and y, and for our torque, we've said that that way is going to be positive for us. So let's take a look now and see how we approach these problems. So we're looking for the acceleration of mass 2. So let's go ahead and step in to where we're going to be able to solve for accelerations. So first off, let's just look at mass 2 here. We know that it's a Newton's second law problem, so the sum of the forces is going to be equal to ma, and that's m2a, right? So what are the forces that are acting on m2? Well, we have tension 2 is the only thing that's acting on us. We just have tension 2 there in that free body diagram. Now, in the y direction, we do have the normal force and gravity, but neither of those are accelerating. So we should probably, just to be specific, annotate this is the x direction acceleration. But that's the only thing that's happening with block 2. However, we don't have tension 2, so we're going to need to figure that out. So let's start looking at block 1. So we also know that we're going to have to do the sum of the forces in this one, in this case, in 1a in the x direction there, because we have defined x based on our coordinate system as going down. We can look at our free body diagram, and we have the force of gravity pulling us down, which is just m1g, minus the force pulling us up, which is going to be tension 1. Now, it's important in this to note that tension 1 and tension 2 are not the same because we have this pulley with mass now that's rotating. So because we have tension 1 and tension 2 and acceleration that are all unknowns, we're going to have to use the pulley as well to try and figure out what these two tensions are going to be. So for a pulley, because it's rotating, we're going to have to use Newton's second law in the rotational frame, which is the sum of the torques is equal to I alpha. Now, we need to figure out what I is. So what is I for a pulley? Well, in this case, if we go up and we take a look in our problem here, we know it's a solid cylinder that they tell us in the problem. So we're going to have to go to our equation sheet and look up what I is for a solid cylinder, and we should see that a disk or a solid cylinder there is I equals 1/2 mr squared. So if we take a look at this and we write this in, 1/2 mr squared for I times alpha should give us what the sum of the torques are, except we also really, we're looking for acceleration, not angular acceleration. So how can we do that? Let's go back, take another look at our equation sheet. If we scroll up, we do have an equation up here that gives us a relationship between linear acceleration or tangential acceleration and our angular acceleration, which is just related by the radius. So if we dive back in to our equation here, we could replace alpha based on that relationship with tangential acceleration over our radius. And now we have that tangential acceleration, which instead of tangential, we could also annotate this as that's the acceleration in the x direction, because our x direction goes around and is tangential to our radius. So there's I alpha. Now we need to find the sum of all the torques on that pulley. So if we step through and take a look, we have tension 2 here and tension 1 here that are both providing torques on our pulley. So if we look at the positive direction, we see we have tension 1 multiplied by R, and they are acting at 90 degrees to one another. So we have a sine of 90, which just goes to 1. Then we have tension 2 acting in the negative direction, so we'll subtract that off. So its radius is also R, and it is also acting at 90 degrees to one another, which goes to 1. So as we step through this, now we can start plugging in some of the things that are relevant to our equation and maybe make this a little bit simpler to read for our pulley. So what this goes to is 1/2 the mass of the pulley times the radius squared times the acceleration in the x direction over r. Well, that over r is just going to cancel with that squared, so let's just kind of touch that up now, make it a little bit simpler to read. AX, that's also going to be equal to now T1 times the radius minus T2 times our radius. And what we should note is that this R is going to cancel. So if we simplify this again, 1/2 mass of the pulley times the acceleration in the x direction is equal to T1 minus T2. Now, we can start trying to simplify and solve for x if we take our tensions up here and solve for them and then plug them in to our equation for acceleration with the tensions in the pulley portion. So let's go ahead and do that now. Basically, we'll take this one and plug it in for tension 2. So we have 1/2 mass of the pulley, AX is equal to tension 1 minus T2, but T2 was just equal to M, this should be M2A. Now for tension 1, we are going to have to do some minor algebra to solve for this. So we have tension 1 up here is just equal to M1G minus M1A in the x direction. So now we have tension 1, and we can plug tension 1 in down here. So if we do that again, we have 1/2 mass of the pulley times the acceleration in the x direction. It's going to be equal to M1G minus M1A all minus M2AX. So once we have walked through all of that algebra, we can now plug in our values for our variables to actually solve for what our acceleration is. So if we do that, mass 1, if we recall, mass 1 was 1 kilogram, mass 2 is 2 kilograms, and the mass of the pulley is 2 kilograms. So this would be 1 kilogram times 9.8 meters per second squared divided by 1/2 times 1 kilogram plus 2 kilograms plus 1 kilogram. And if we step through all of that, what we should find is that our acceleration is going to be equal to 2.45 meters per second squared.